all n plus 1 tuples such that the product is 1. So I can identify then these one parameter subgroups with this free Z module here. So if now here lambda equal to lambda 0 to lambda n, and x is then defined by, and x is defined by these polynomials f1, fs, then belonging then to this homogeneous coordinate ring, then this variety then here x in order to define this function, so I first then define this degeneration here, is a limit when, is the limit when t goes to infinity of then the family then. So I have a one parameter family of such varieties of dimension r and degree d. So I have then here, take then this function here, but now I deform the coordinates with this t power. So I have then here x0 unto t lambda n, xn, and then the last equation here, fs. And then I have t lambda, I do the same thing everywhere. So if you put 1 everywhere, then you get your variety x back. And if you put, if you look at when t is different from 0, it's still isomorphic. So what this is a fiber. So x lambda is then the fiber at t equal to 0 of a test configuration, of a what I call a test configuration. I mean, it's called a test configuration in the literature. Test configuration, then, so I have a full family of A1, where then all fibers, and here, all fibers, and here, T at T which are different from 0 are then isomorphic to, they are isomorphic then to X in Pn. Because you have an explicit information then given by all this. This is then just a coordinate change, a linear coordinate change, and they will all be isomorphic to x, except when t then goes to infinity, then you get a degeneration. And in order now to define this function, you rather look at this degeneration, which is then, so for each such integral n plus 1 tuple, you get a degeneration, and then you can use that to define this weight function, and then by some homogeneous property you extend it to q, and then it's continuous. So can I erase it, or?
Well, you can erase.
Yeah, okay, I do that first then. Okay, let's do that. See for the. So now then, just to remind you what we did yesterday is now that this GM, I mean, I gave a more abstract intrinsic definition of this, it's clear that everything is GM equivariant. So GM then, but it's clear from this description as well, GM then acts on the homogeneous coordinate ring, which I then will then call S lambda. So this is has a natural grading Sk of lambda, and this is now equal then, given by a homogeneous ideal here, I lambda of x lambda. So now we can now define the weight. So this is how we get then this definition for the integral part here. So this function then here is now the weight. This is now the weight of the of the GM action on this vector space. And this means that this is now equal to, I take the minimum over all monomial bases. So I take all these monomial bases here, A, H, K, try to write a bit bigger here. And then I sum over all weights of the individual polynomials. So I have then here X. So this is vector notation. So I have an n plus 1 tuples of non-negative integers, and then I can form monomials. And and then I take the weight of this, the weight with respect to lambda of each monomial, A of I, where then this weight of X of A of I is then simply that you take a scalar product of this n plus 1 tuple. So you have lambda 0, A, I 0, etc. And then you have lambda n, I, A, n. And these xi, these vectors are running over all monomial bases. So, and this xi a1 up to then here x a n, a hk are running over all, monomial bases of this sk lambda. So that is then the definition of this weight, and this is studied in detail in Manfred's book. And what we will do in a moment is that we will let K study how this varies when K takes different values, and then we will get some kind of Hilbert polynomial, and we will see that the leading coefficient is this chow weight. But I will come back to that. So what more did I want to say? Yeah, so before I do that, I then want to do the basic lemma, how to bound this determinant here. So we have then here the following proposition then here. So let then here hk be then this dimension of this part k of the coordinate ring of x, but this is also equal to the dimension of this deformed code, because it's a family, and I mean this will be preserved. So so now then I would like to I will not really need this in the statement. For then what do I write here? Yes, no, it's correct. For then the coordinate ring, did I introduce it? No. For the coordinate ring S then of then x. So it's just a Hilbert function here of degree k on this homogeneous coordinate ring of x. And then there exists, the claim is then that there exists a monomial basis with small determinant. So then there exists a monomial basis x a1 up to x a h of k of this part k, the homogeneous degree k part of this coordinate ring of x, such that this determinant I'm interested in. So I want to bound this determinant x. So now I evaluate this polynomial then here. So I have then here a monomial. I have then a hk monomial, and now I will evaluate them at the same number of points, x h of ak, and then I first evaluate it at the first point p1, and then the last point here, and then I evaluate it here p1 and up to phk. So I really want to take the absolute value of this determinant here. I don't know how to write it. yeah, I skip this. I mean, you understand what I mean. So this is now smaller than. So I just use then the, if they were all equal to b, then it would be clear that each term here would be bk. So then I would get the following trivial bound. I would then get here bk times h of k. But what happens now is that I will get an extra factor due to the fact that this is lopsided. So it will not only in general, when it's unstable, it will not in general depend on the just on the volume, but there is this extra function which has then Mumford's weight function. So this is now just you take log of b0, b, and then now the sum here will be 0, where then this b as before is the mean value here. And then, so this will then be true. And so maybe the order of the word phrasing here is not correct, but for any, the grammar is not correct, but sorry. So this is, I put this in brackets. And for any p1, p2 be lying in this box. Then. So I look at integral points lying in this box, b1. So there is nothing with congruences yet. So it's I just look at point lying in this box. So the idea now is that I want this determinant to be 0. So there are two ingredients. First, I have to bound it, and secondly, I have to find a p factor which is larger. And then it will turn out that this determinant will be 0. And then some linear combination of these monomials will then vanish on all those points. And since they vanish on all those points, then the whole thing, all those points rely on a hypersurface of degree k. So what I wanted to do now is then to give a proof of this, because I mean this is really the key. I mean, so I have to find a razor first, otherwise I can't give. Ah, there. Okay. Thank you. Sorry, you have to speak louder because.
May I ask why we have a factor of HK factorial on the right-hand side?
Why we have that?
Yeah.
I just take the definition of determinant. So in fact, what I will do is just that I will bound, say, the product of the diagonals or so. And
So you just add up everything.
yeah. So it's. But you're right, I don't really want that one. But so in these later estimates, there will be a b epsilon factor. And one of the reasons I will add the b epsilon is that I want to absorb this hk. I don't really want it, but you can, yeah.
This term sounds very large.
No, but the point is that it will be, I mean, it will not depend on b, so.
Oh, I see your point.
Yeah. Yeah. And it will not be that large. I mean, so anyway, so everything, it can be, the main point is that it can be absorbed in this b epsilon. So it would be harder to absorb it in a b log factor. So there are some final results where you have log b instead of b epsilon in this, my main result. So you have a point there, but if I have b epsilon, then everything is under control. So as a first approximation, you can just forget about this factor. I will take care of it. Yeah. So the proof is not more or less follows by definition. So the main reason I state it like this is that I want to. This gives me access to Mumford's book. I mean, so Mumford studied this function is already understood, and so when k. You get the polynomial when you vary k, and the leading coefficient will be then the Chow coordinates. So this is why it's so useful to formulate it like this. But it's not a deep result as such. What's deep is rather to study this function wk. That is deep. Okay, so let me give the proof. So So you can always approximate any real n+1 tuple by a rational n+1 tuple. So we may assume that, so because it's continuous, so if it's true, then in that case, then we are done. So we may assume that this log b of I belong to Q by continuity. And find P, I, and Q such that I will then have that BI, if I divide it by, let's see here, such that, yes, this log BI of B is equal to PI divided by Q, and that is that we have that B can then be, BI can then, this bound can then be written as B EPI divided by Q. So this looks artificial when if you're an analytic number series or anything to write it like this, but this is a way forward, because then if you only first consider this case, then you can relate it to this function and to integral n+1 tuples where you have a complete understanding of this weight function. So therefore, it's the weight. And I've not studied this other paper on different approximation by Varieties, but I think they do exactly the same way. So it's very, very natural. So they appeared this paper. I mean, this is just a dressed up version of what we did in this paper, in these papers in Krelle 2003, 2004, and at about the same time they published their paper. And it's only 14 years after I realized that those papers exist. I've given talks at many places with famous people like Bombieri, who knows both theory, but no one remarked it. Told me that there is a link between these two. So, okay, so these then weights then you can look at the weight of this, because now if you know, we then have to consider the weights of these rational numbers. And since it's kind of homogeneous, we only have to consider weights of this integral n+1 tuples. So then the weight of P0 up to Pn is then the lowest T power n, is then the lowest T power in this product, where I take the product from 1 to h of k, and I then evaluate these monomials at the L tuples. I mean, so now the L tuples will look like that. I use the fact that the bounds are of that form. So instead of plugging in the explicit coordinates here, I plug in, say, here B0, B1, Bn. So the estimates for each term in the determinant will be the same. I mean, there are hk faculty such terms, and I use the same method to estimate each term, that I plug in here B0, B1, etc. And then I will get, and then I want to estimate that. And then to do that, I first look at an expression in T, and then I will then have TPN. Then this is the lowest. This is then this is the lowest T power in this expression among all monomial bases, more or less by definition, of sk lambda. So you can say that is how we define it's just a redefinition, reinterpretation of the definition I just gave. But now comes the main point. We made this deformation, degeneration of this ordinate first variety x to xk to x lambda. And what happens now is that this sk lambda, you can, so to say, define, just as we define Chow weights by expanding with t and taking the leading coefficients, we can do the same thing here. I stated that as a lemma. Now, actually, if you take them, you can do the same. You can do the same game here with look at monomial basis of xk, and then it will be the same outcome. So it's also true, and also among all bases of xk. So I don't think I want to spend more time on saying that. It's easily checked if you are used to this Gröbner basis thinking. But that will be used because in this determinant here I have something. I'm looking at monomial bases in the coordinate ring X, but this term here is defined, so to say, using monomial coordinate rings of this degenerated variety. So I have to make a transition. And it's the same in this paper, Evert Seferetti. They also make a transition. So to some extent, this is easier, this degenerated ring. Because if, for instance, all those log of BIs, if they are Q linearly independent, then it's just a monomial ideal. So you should think of this as a monomial ideal, as this x lambda, that it has a very simple description. And that will be used at a number of places. It's simpler to deal with. But what we use here is just that this definition is the same whether we take monomial bases of x or xx or this deformed ring x lambda here. So now we just have to plug in then this particular value that now. So now just insert t equal to E1 of k to conclude that. So now I can then bound. I mean, each say if imagine say I want to bound the product of the main diagonal, then I can bound it by the following expression. To conclude that so now I take the product then of this. I have then all those monomials, that many monomials, and then instead of plugging these values, I plug in these larger non-positive values. So then what I will have to bound then will then be this A J0. I take the product here Bn divided by B, and I have then here Aj of n. So what I have found now is that this will now be smaller than x of, what I get is that this is smaller than x log of this B0B up to log Bn of B. This is then concludes the proof of this. So this is a method I use to bound, I mean, this determinants. So now the next step is now to understand this right-hand side. What happens asymptotically with this bound when k goes to infinity? And now I will use a lemma in Mumford's book, or maybe rather it's in this L'enseignement mathématique, a paper called Stability of Projective Varieties. So here you see I have this Hilbert weights, but in the statements, the theorem I stated on Monday, I have Chow weights. So now it's a great thing that I will use Salt by Mumford. So this is why I stated this in this way. Yeah. Yes. Yeah. Thank you very much. You're absolutely right. And this happens to me quite often that I say one thing and then I write something else. So sorry. Thank you very much. Okay. So now then, I think I can. Can you take it down? So or yeah. Yeah, okay, I erase this. In fact, I don't need the proof anymore. So I don't know how what makes you say that the lemma is more funny than another lemma, but I think this lemma is called Mumford's droll lemma. And droll, I think it means the same in French, drôle. So I don't know why it's so funny, but it's called Mumford's droll lemma. Maybe there's something I missed, but anyway, I think it's quite well-established name. So, what?
Strange as well. So
Yeah, drôle, oui.
maybe it means strange.
Ah, French lemma, yeah, I don't know. Okay, so to relate, yeah, Hilbert weights of this Hilbert weights to the Chow weight then we use the following. So it's called Mumford's droll lemma. So it's on l'enseignement mathématique 1977. I don't remember, did I write this page here? I can't read it. No, it's lemma 214. Lemma 214. So let then here lambda belong here to Hom Jm of t. And this is now, as we have seen before many times, equal then to an n plus 1 tuple with some 0. And then we have this y weights. So let me write it like this, w k lambda x. So I will skip this x because x will be fixed. I mean, all this function will depend on x in general, but since I will only consider one variety now, I will just skip x. Be as before. Then there exists coefficients and ai of lambda belonging then to z. So you have then 0 y of r plus 1. So now we will show that this is a kind of Hilbert polynomials and k0 of n, such that you have that this weight function, it will be polynomial when we vary here, so it will be a polynomial degree r plus 1. So of course these coefficients will then depend on this weight, but the first term will then be, so this is when you have an integral valued functions, instead of writing it as a polynomial, it's standard that you write it in this way. So instead of writing kr plus 1, you write it in this way. And then you have then a r of lambda. Then you will have k over r. And finally, then you will have then a1 of lambda, k of 1. And then you will have then here plus a0 of lambda. So when you vary k, you would get the polynomial of degree k plus 1. And the main point is now that the leading coefficients here he shows that this has this interpretation as a Chow weight. I mean, the Chow weight I defined in my first lecture, and which was a statement of the theorem. So then the existence. So this is then 4k at least. I mean, usually when you have a Hilbert function, it's not a polynomial at all k. I mean, for negatives, it's certainly not. But when k is at least k0 for sufficiently big. And moreover, then, this AR plus 1 of delta, then, is the Chow weight. Chow weight of x with respect to lambda, and which I then defined on which I then defined on Monday, 2 days ago. So I will not prove this lemma, so I will simply use it. I mean, it's extremely useful because what you do here is that you don't know at which k this determinant will become 0. So to prove that there is some k for which it is 0, this determinant, then you have to make an asymptotic analysis of this function here. So you have to understand the asymptotic behavior of that. So all this was done in these papers by 15 years ago in Krelle by Beruba and myself. It was just that we didn't have this nice interpretation of this function. So we did formulate the Hilbert polynomials, but Beruba then, I call it the Beruba invariance. But in fact, these Beruba invariants were just these Chow weights. And that was not clear to us because I didn't know about this Mumford's draw lemma. So let me just make you some further remarks. Because we have high ambitions here, we want to have everything uniformly. Because now many things here depend on x and when you define it, so it's not clear that this can be bounded. So you should view this as error terms. So you want to control them. But you don't want to have bounds which depend on x. You want them to have uniform bounds. And then you have to do some extra work, which goes a little bit beyond what Mumford did. So let me then make some remarks here of what you have to do. So first this K0 can be chosen then, independently of x, and only depending on independently of x and lambda also. So it will only depend on it will then only depend on these parameters r, maybe d and n, and I can even skip this d, r, because r is bounded in terms of n. So that is very important because I want to have complete uniformity when I do induction by dimension, when I apply this estimate. So that is quite hard. So in order to do that, you really have to use some Gröbner basis techniques and so on. And another thing you have to do is that you also have to bound the coefficients then. The coefficients then here, the non-leading coefficients, AR lambda up to A0 lambda can also be bounded uniformly, can also be bounded uniformly. So this is what's often what makes things hard, because I mean still you can learn Mumford theory. I mean it was great when it came, but it's not, you don't have to be that clever to understand it. But I mean to do all these things uniformly, you really have to work. But you have these techniques from Gröbner basis theory, so you can give uniform bounds here. So in fact, in this paper by Everts and Ferretti, they only give bounds on one direction. So what Brubai and I did was, in fact, better because we used some theorems of Gröbner basis. I don't want to go into that, but this is a technical point. You have to control, you want to have a complete control of these coefficients here. And I should also say here that there exists a continuous extension, of course. There exists now here a unique, continuous extension then of I mean with the natural prop of the AR plus 1 of lambda then given, so to say, by the Chow weight, given by the Chow weight defined on Monday. I mean, defined last Monday. So first we prove when it's integral, it is a Chow weight, but I defined the Chow weight also for, I took then non-integral exponents, and then I expanded it in terms of t, and you can do that. There is only one natural extension to the reals, because here in Mumford's lemma, it's only for integral n plus 1 tuples, but I mean you can give a meaning, you can extend I mean the leading term here to the real. And yes, so the main point is really that that this is Shao. I mean this is Shao. If you look at Mumford's book, I mean there are two kind of when you have families of varieties, you can either use Hilbert schemes or Shao varieties. So both occur in his book, but in the book I don't think there is these precise relations, but that you find in this paper. Okay, so now I think I will this ends my description of the techniques to. So the whole point is then that all those stuff here, it can be written as O d of n of k of r. So this is what I will what will be used. I mean, that I can have this uniform bound here, independently on x and coefficients and everything. So now then I want to come now to the p-adic part here. So it's just that maybe I should still maybe make some comments about if you want to look at this paper of Broberg, maybe still I want to say something about his approach with the previous paper, so you can, if you read them so that you can relate them. Just I have such a mess with all my papers here, so let's see if I can find it. Yeah, okay. So let me just say a comparison with the existing literature. I mean, so I maybe I plan to include this in this, if there will be conference proceedings, maybe I will include this new formulation of this determinant method. But for the moment, just equivalent to what is in the literature in this Krelle paper. So let me just give you some remarks. So let me first tell you about graded monomial orderings, which is closely related then to Grosvenor basis. So what I did here is that I degenerated the variety to a variety which was then defined by equations with fewer monomials, you can say. Some of the monomials will disappear. But you can also do something similar by using graded monomial orderings, and then you replace the ideal, homogeneous ideal with the leading terms. And actually, when these log of BIs are linearly independent, it's the same thing. So this is why this here is. But let me tell you what the graded monomial ordering is. So you have first that this should be a total ordering on Z, then n plus 1. So I have a total ordering among all n plus 1 tuples of non-negative integers here. And then, secondly, then I should have that this ordering alpha should always, a vector then, if I have an element here, is always bigger than 1 for all. So this is a 0 vector for all alpha belonging to set n plus 1, which are non-negative. Third is that if you have 3 such n plus 1 tuples, and then you have then here z n plus 1, 0, then you have that if alpha is smaller than beta, this will imply that alpha plus gamma. So you take sum of vectors, and then this should still be true. And the fourth axiom is now here that if alpha and beta belong to z n plus 1 of 0, then, and if you have alpha smaller than beta, so then the degree of alpha should be smaller than degree of beta. So the lowest one are always of degree 0, and then comes the one of degree 8 and degree 1. So what do I mean by degree? So the degree of alpha is now equal to alpha 0 plus alpha 1. So it will correspond to the degree of the corresponding monomial. So you should view them as exponent of monomials. So I will study monomials, so I will get the ordering of monomials, and the smallest one are then on degree 0, and then I have an order between degree 1. And one, of course, ordering is a lexicographical ordering, just in the phone catalog. So, but I don't want to give examples, I just state this. Yes?
You ask if it's a well ordering that you don't have an infinite decreasing sequence?
That I don't have.
Do you ask that the order is a well ordering that you don't have an infinite decreasing sequence, or you don't ask the
No, I don't. This is all the axioms I will need to make this work. And so I just will tell you now that if this log are B0 or linearly independent, this is a generic case, then there is one natural graded monomial. So what Broberg does is that he defines such Hilbert polynomials for any graded monomial ordering. So Broberg defines Hilbert polynomials, similar then to this Vk goes to Vkx of lambda. That was the way I think I wrote it. For any x and any then lambda 0, lambda n, but this is then just as before. It's still given by this log of this bi divided by b. So he has the same data. Moreover, he also adds any such ordering. So it's not just that he has one set of polynomials for each variety in each such box. So I mean, these tuples, these weights are defined by the box and by the variety. He also has an extra data that there is a graded monomial orderings. But in fact, his result is only really useful if you take the best choice. And there is one very natural graded monomial ordering. If, say, this log B0 up to log Bn are linearly independent over Q, then there is one natural optimal ordering. Then there is one natural then optimal ordering, I mean such graded, where then you have that will then have that alpha smaller than b, degree alpha equal to degree beta. This is then equivalent to that. This is true if and only if you just plug in these values, b0 alpha 0, and then you have bn alpha n. So evaluate these monomials at this point, and then if this is bigger than b0 beta 0, bn beta n. And now the point when then, if then the degree of alpha is equal to the degree of beta. If the degree are different, of course, you already know that the one with the higher degree should be bigger than the smaller degree. So this you can show that this defines a graded monomial ordering. And if you chose this graded monomial ordering, you get the same invariant here. So this ordering gives the same monomial Vk lambda x as in these lectures. But what Broberg did was that he noticed that if you just have a graded monomial ordering and you, so to say, then do the same constructions as here, you always get the such polynomial. You get an analog of this Mumford-Strolls lemma, but he didn't have this interpretation of the leading coefficient. So I just call this a Broberg invariance. But in fact, the approaches are equivalent. It's just that I have a nicer formulation now thanks to this Mumford's lemma. But I still can't use Mumford's book, I mean, to have all these uniformity statements. So still, I mean, the main job was already done, I mean, in his paper and to some extent in my paper. There was a few details lacking. So my paper is on archive, this Krelle paper, if you want to have a look at that. So I think that now I have really given a very detailed discussion of how you can give make the upper bounds. One thing I would plan to do was to say how is this invariant related to Heath-Brown's invariant. Maybe I should do that as well, because this Chow form here is still quite complicated, so maybe I should still say something about that. And then I will turn to the p-adic aspect, I mean this factor. So let me just take a comparison then, comparison with Heath-Brown's exponent for hypersurface. So I have to compute this Chow weight then. So I did not redefine the Chow weight, but I think it will be clear from what I will do now. So let me see. I wanted to. So I first remind you of the definition then here. So we had then here, I looked then that, I let then here that fx, if then fx is the Chow form of then this x of Pn, then and if I have then here this C is now equal to C0 up to Cn, then what I did was then that I expanded this f of x, and so here this C will be log of B0 divided by B, etc. So I then plugged in this exponent here, so I had then here T0 of A00, etc. And then I had this, because the Chow polynomial was given in terms of R+1 complementary hyperplanes. So for each hyperplane is then I have then coordinates of the hyperplane, and then I perturb this by this one parameter subgroup, and this is how I define the Chow weight. So I just repeat now the definition I gave on Monday. So the last one is then I have R+1 hyperplane, so I have a function in R+1 hyperplanes, and then the hyperplanes are defined then by the coefficients of the linear equation they defined. So it looks like this. And then I expanded this by, so I had then here T of something, I'd say A0, G0 plus T A1, etc., J1, etc., where then A0 is then smaller than A1. So this is then the Chow weight. This is then the Chow weight of x with respect to this C. So in the applications here, when you look at the theorem, C will be this log B of I. So now, in general, it's very hard to compute this Chow form. It still may be, I don't know what is easiest to compute, this or Broberg's invariance. It's just that the Chow forms is more elegant. So maybe still this Gribber basis techniques, maybe still you can make an algorithm, you can still make a computer program on that. But at least for hypersurfaces, it's easy to compute, because you can show that there are two ways of defining this Chow There's another version of Chow coordinates where instead of taking r plus 1 hyperplanes, you take just one plane of codimension r plus 1, and then you look at the subvariety of dimension 1 in the Grassmannian instead. So you look at the Grassmannian such that a generic hyperplane section, a generic plane section is 0. So if you take r plus 1, codimension r plus 1, the generic section will be empty. But there is a subvariety of codimension 1, which then gives you another version of the Chow coordinates. And it turns out that this polynomial here is given by determinants. So in particular then, if then here x of Pn is a hypersurface, then as always, this polynomial f of x, which is then given by h, you have then here h0, you parameterize like that, hr, is then given by r cross r is then a function of r cross r determinants, r cross r minus of this matrix, say h equal to h1. Shall I put them? I can put it like that. h1 up to hr. So I look at h0. So I have an r plus 1 n plus 1 tuples, but I can then look at such minus, and then so this polynomial is not any polynomial. It can be described very concretely as a polynomial in such indeterminants, and because it's equivalent to the other definition of Chow coordinates, and in particular in this case, explicit description of the Chow form. If you have a hypersurface, everything simplifies a lot. So I just have to. I wanted to just to state this. So sorry if I'm a bit disorganized here. So I start to get sufficiently so many papers. So 4, 5, yes. So I have now the following, that if now this x is defined by a hypersurface, then I can give you an explicit formula for this Chow form, which is very hard if you don't have a hypersurface. So this may also give you some idea why Heath-Brown's case still is easier than the case of high dimension. It reflects the fact that the Chow is easier to compute the Chow form, so easier to describe. So I just wanted to make this computation because otherwise it just look like a mystery, this form. So example then. I will then have there. So if now x equal to xd, Pn is then r equal to n minus 1, is defined by, so I have then an explicit description of this defining polynomial. So I have then here various n plus 1 tuples, and I have then here coefficients a0 up to an, and I have then here x0, I0, xn, in. Then the Chow form, then it's Chow form. Here you can think that you don't really need any Chow forms because, I mean, you already have an equation. But, I mean, you can easily relate them such that my theorem contains Heath-Brown as a special case. So then these Chow forms is then just the same polynomial in this minus of this. So I have maybe here a sign problems, but this will not matter here, so I don't care about the sign. And then I write it like this. So this will now be here then 1 of n. I will notation you find in classical text in algebraic geometry, like Hodge-Pedo and so books written in the 50s. I will explain you this notation here. 0, n minus 1, I of n. So these are these minus I talked about, where then this J1 up to Jn is now equal to here the determinant of h 0 J1 up to h 0 j of n, etc., up to hr. So I have then here J1 up to h r Jn. So for each of those vectors, you just pick those coordinates in h1, in h2, and here you just pick those coordinates, and then you form these determinants. So you see the Chow form is more or less the same as the original polynomial. And now you can see what happens now if you plug in t here. Then, of course, this will get multiply according to the exponents here. So it's very easy to see what happens when you make this expansion here. And then you get then this the following formula here. So from this you see that this invariance a of x of c, it will actually be equal to a minimum. So here I will run over all those monomial bases, and then I will get the following expression, j equal to 0 goes to n, and then I will have this, I will look at each position then, how the effect of t, and the outcome now will be the following. I will now here have the sum, where I have then here k goes from 0 to n, and then I then have to exclude one term, and then I take the sum of this, this sum here of this ck here. So why do I get this? Well, if you look at this, you have at each you have this expression here. So this reflects the fact that I have omitted then here the 0 coordinate, but so I omit here first the 0 coordinate, and then I omit the 1 coordinate, etc. And here you have this exponent of these monomial bases. So this is then here again running over all these monomial bases. So this in its turn can be written as d times c0 plus cn minus then here the maximum. And now maybe you recognize Heath-Brown's invariance here, where you then have I0 c0 plus in cn, where those I indices here, where those I0 up to in, these are then running over all those indices here, I0 here up to in, which are then equal to 0. So this is what happens. I mean, only those coefficients which are non-zero, I mean, will contribute, of course, to this expansion. So I only have to consider them. So this is I just use this formula, and then I get this expression. And now, once you have this formula, it's very easy to see that that this is you get exactly Heath-Brown's expression. I could do it. I have just 2 lines, but I think I've already talked too much about this. So I think I want to stop now here with the Archimedean part, but this was just to tell you that it's very easy to show that my theorem is compatible with Heath-Brown's, and this compatibility depends on exactly on this computation and on this formula here. Okay, so let me then now switch to the p part, and then I think I will now just take the cubic box. I mean, you can combine any boxes with this p factors, but I mean, in order to avoid technical details, I will now just assume that we have a hypercube. I mean, it will not influence the p's at all. I mean, the argument will be the same. For the p factor arguments will be the same independently on the box. The difficulties with lopsided boxes have already been treated, I mean, here. So So from now on, I can just assume that I have a hypercube. So otherwise, it's so cumbersome to awkward with all the technical details. So it's quite amusing when I looked at this varieties. So there are so many similarities what they do. I mean, they use similar techniques. So, but the context is completely different. I mean. So one of the reasons is that I always find that there are many more people working on the Fantan approximation. So I thought that if I compared my result with results in Fantan approximation, I would create a bigger interest. But for me, rational points are more interesting. But I don't know. Anyway, it's always nice when mathematics is connected, you find similarities between different areas. So I really appreciate the Boss's introduction of thermodynamics. So that was fantastic. Okay. So I tried to do something similar here on a lower level. So now then I will go to the aspect of then of the p-adic factor then here. So now we have the following situation. So you can more or less forget what I did until now, because now it's a completely different problem. So now again, I repeat that this is still now here a closed subvariety. And you have then here that the degree of x is equal to d, and the dimension of x is equal to r. And then I have then here that I have then this coordinate ring as before. S is then here the coordinate ring sk, k go 0. And I have then here that hk is equal to the dimension of sk. So now I will introduce a singular point. So this is a scheme theoretical closure then, which I reduce modulo p. So the problem now I'm interested in is then the following. Find a high p power, find a high p power as high as possible. P j of k with this j of k. It should not depend on the variety here. It should just depend on these parameters, depending then only on d, r, and n, such that p of j of k divides is determinant of f of I of p of j for any. So here I will not really need that they are monomials. I will apply it to monomials for any homogeneous polynomials. Homogeneous polynomials. F1 up to then here fhk. And the situation I will apply it will, of course, be when they form a basis of sk. But I mean, my argument will work in any case, so I do not have to assume that they are a basis. But I mean, I will apply it to a monomial basis. So they will now be integral polynomials for homogeneous polynomials of degree k. And points and any points p1 ph of k. So now I will have integral points. Maybe I should write it. I use abuse of notation here, so I write set point of x, but then I mean an integral point on the closure. So those points are in one-to-one corresponding with rational points on the on X. So, but I write it like that. And then I look at those which reduce to Y. So these B's will, of course, play the Archimedean size of the coordinates will play no role when you look at congruences. So the only thing I'm interested in is then that they reduce to the same. So that is that I have that I have the followings, that I have that those points P1 modulo P, when you reduce modulo P is equal to P2 modulo P, etc. is equal to PH modulo P, and they should all be equal then to the given points in X P of FP. So this is my hypothesis. So you can also view this as a box, but it's now a p-adic box. I mean, so they are closed p-adically instead of being in Archimedean box. So then the motivation is, of course, the following then, which I've already explained. So motivation is then that if now we choose now P1 PHK, if they also satisfy these conditions, then X of Z. So now I will only consider hypercube case for simplicity. Then we have that this determinant then of this f of I, P of J. If you have this and this F1 FHK are monomials of a degree of k, then if I just take the trivial version, so then you have that the determinant of this f of I of P of J, then this is, we saw in the simplest case we had before, this is just equal to HK faculty times BK of H of K. I mean, you just look at the definition of determinant, and then each is so many terms, and each terms you just have HK factors or polynomials or monomials of degree k. So you have this trivial bound. So if now you can produce a factor now which is bigger, so if P of J of k is bigger than this HK K of H of k, then this determinant is 0, then this determinant of this f of I of P of J is 0, and we get then here, and at the end we will then get that X Z of B of I is now contained in a set, a hypersurface of degree k, while we will have that X itself is not contained in Z. So this is a reason I'm interested in this. So I want now to produce such high p factors in such these determinants I just considered. And but for that, I don't need that they are monomials, and I don't need that the points are in this box. So I just need this hypothesis that they should be of the same degree, the polynomials, and I need that the points reduce to the same class modulo p. So what will happen is that we will this can be achieved here. So I just so this can be achieved when P is sufficiently big compared to B. So we have then the following, that this can be achieved if P is at least B R plus 1 divided by R d1 over R plus epsilon. Then K will be, this hypersurface will be bounded in terms of dn and epsilon. So if what I do is that sorry, epsilon should be here, of course. So if I fix now an epsilon, so I fix this data, epsilon d and n, then it's true that for any prime p and for any variety x of degree d and dimension r, then there exists a hypersurface of degree k bounded in terms which, contains all those points which specialize to any non-singular point modulo p. So this is a statement. So I hope now you see the motivation. So now the point is now that this means that if I divide the set of points, instead of counting all points in the box, I count only those in a congruence class. But after that, I can sum over all congruence classes modulo p, and then I get a reduction from, say, a problem for surfaces to a problem on curves. So then I can reiterate this process, and finally I get the estimate. I can do it in any dimension, and of course it's wasteful if you do it too many times, but it's still often the best thing you have. So now I will completely concentrate then on this p case. It's just I have to control. I don't want to have no interest. See, I still have 10 minutes, I think. What is the time? 10 minutes or 6 minutes? What? Because I can stop now. I'm a bit tired anyway. So I don't want to insist at all. So see what I can say in a reasonable number of time, because there have already been many technicalities here. So let me then give you the solution here of this problem. Is just I would like to have more blackboards, but okay. So solution of problem, or then this p factor problem then. There is one very standard solution where you just use the p-adic implicit function theorem, and this is a bound which occur in all our previous papers by Heath-Brown, myself, and Broberg, and so on, and then you get this exponent. In some cases where you are lucky, there is a more sophisticated approach where you use a global geometry, and you have to use the Lazarsfeld volume function. But I will start with this simple approach where you get still a good p factor. But then it's convenient to first reformulate this and to reduce it to a affine problem. So after then permuting then these coordinates x0, xn, then we may assume that the first coordinate that p does not divide x0 of p of j for any j for any p of j. They are all congruent, and they must have some p coordinate which is non-zero, and since they are congruent, you can choose one which is the same for all. Another way of phrasing this is you just look at the coordinates of y, and you choose one coordinate with fp coordinate of y which is non-zero. So this means that x0 of y is different from 0 in fp. So this is convenient. So then now what I do is now that when I look at this determinant, I can just divide by a suitable factor of x0. So I can dehomogenize the polynomial. And then I just get an affine problem. And then I can use ring theory or so, implicit function theorem. So it's easier to rephrase this as an affine problem. Because since this is not divisible by p, it will not affect the p factor. So I will use that now. Look at the affine subvariety where this x0 given by where this is non-zero here. So we may assume that this. So let then here y tilde here in a n of z, be then the principal open subscheme, d plus x0 of x. I don't want to with then affine coordinates, with then affine coordinates y of I divided then by xi of x0, where then y goes from 1 to 0. So then you can view these points as P1 up to P h of k. They will all lie on this principal open subscheme. They will not be z point anymore because you divide by something, but they will still be set p points. So this is now here the local ring at Q, local ring in Q. So you localize such that you have the local ring at P. So then if you look at these coordinates, these coordinates will lie in this ring. So in fact, I will not need that I integral anything. So I can now just look at such a problem, try to prove that there's a p factor for any such set p points on this affine scheme here. And I can also, if I want, complete this, I can embed this in the p-adic completion. And that's convenient because then I can then use the p-adic implicit function theorem. So this is what I will do. But I will do this in detail on next time. So I will discuss the p-adic problem. There are also interesting complications because if I want to go beyond this method with implicit function and use a global geometry, then I will get an invariant which also occurs in the affine approximation in a paper by McKinnon and Root. So I invented it in 2006, and suddenly the same invariant popped up in some years later as a generalization to Root theorem. So I would like to discuss that as well the last time. And so what I will have then is I now have a new equivalent problem. And this is then the following. So what I will do now here is that let then here f of I say y1 up to then y of n be equal then to f of I 1 of y1 y of n for all I for then so then when I have 1 y divided by h of k. So I dehomogenize everything. So then the problem is then the following: find a high p factor p of j of k of this new determinant of this. And now everything is much simpler because it's just affine, and these are all well defined. I mean this determinant here. So what I do now here is that I make now here some linear substitution. So is my time out and I stop? 5 minutes? 5 minutes, okay. Okay, so I will. I mean, this is not hard. I mean, this is much easier than, less technical than what I did before. So you see, I will never use that I have monomials here, but I will apply it to monomials. So the solution then to this new equivalent problem is that I make, after some linear substitution, after then linear coordinate change. So then I I let this y1 goes to yy minus the point of this p1, then we get that they are all congruent to 0 modulo p. So then we get that y1 modulo of p of j, etc. is coordinate to y of 2 of p of j, and this is then congruent to y of n modulo p of j, or this is then congruent to 0 mod p for all j belonging to 1 of h of k. So this makes, of course, it's more likely that I will have p factors when all the coordinates of all the point will be here of order p here. So we will be congruent to 0 modulo p. So I can always assume that the points I studied just by coordinate change, it will not affect the determinant. I can assume that I have such coordinate. Another thing now is that by the implicit function theorem, by the p-adic implicit function theorem, then we may we may find a subset of our coordinates among those n coordinates, y1 up to yn. And now, since it's true for some coordinates, I can just rename them. So I choose the first r1, say y1 times yr, such that the remaining one lies in this formal power series of the first ones, such that r plus 1 up to I of n, the other coordinates, just lie in the formal ring of power series y1 up to y of r. So this is very useful information, because this means that all those polynomials, they are also formal power series in R variables. And this, I think, where I will end, and then I will finish this next time. So hence we get that these f1, no, sorry, these functions f1, fhk, since they are then integral combinations of those coordinates, or polynomials with integral coefficients, it means then that they also either get p of y1 and y of r. And what I will do then the last time is then I will start then solving this problem and with this extra information that I will have to prove that there's a high p factor in a determinant where all the coordinates of all the points are congruent to 0 modulo p, and which I evaluate then at that many power series. And then it's easy to see that you can do eliminate. So you only need a constant coefficient for one. All the other ones will lie in this ideal generated by y and yr. And all but r plus 1 will lie in this square of this ideal, etc. So it's quite easy to prove then that there is a high p factor. I mean, using elementary transformation in this determinant. But I will explain that next time. And okay, I stop here.